Okay, in this video, I'm going to show you how to get the answer to the speed of the space station at an altitude of 400 kilometers. So the space station's orbiting. And I'm going to go through everything. Okay, I'm not going to pull any punches. I'm not going to start it from any special point. I'm going to start from mostly scratch. I'm going to use a couple of principles, and I'm not going to use vectors just because I want to make this as straightforward as possible. We can do this without using vector notation. So everything here is going to be no vectors. Okay, let's get started. Okay, so I have here the space station orbiting. There's the Earth. I drew that myself. And this is 400 kilometers above the surface of the Earth. Now, what's the first thing we need to know? We need to know the relationship between force and acceleration. So in one dimension, okay, then I can write the following. This is called Newton's second law. F net equals ma. So the total force on an object is equal to the product of its mass and acceleration. And the direction of the acceleration has to be the same as the direction of the force. That's big idea number one. Number two, the gravitational force. If two objects have mass, let me draw it over here. Here's M1 and here's M2. And they are separated by a distance r, then there is a gravitational force pulling these two together. So the gravitational force, we'll call it Fg, is equal to g m1 m2 over r squared. Now, this is a scalar vector force. A lot of times we'd want to write this as a vector, but I think for this purposes, I'm going to just use it as a scalar. This says that the force pulling these two things together depends on g, the gravitational constant, which I'll show you in just a little bit, the products of their masses, and the distance between them squared. So this is the distance r. Okay, that's big idea number two. Big idea number three. If an object is moving in a circle of radius r with a velocity v, then as the object moves to a different location, it's going in a different direction, but still has the same radius r and has the same magnitude of velocity, but different direction. So that is indeed an acceleration. Acceleration as a vector, okay, I said, I lied. I'm a liar. Okay, that's fine. It's going to be the change in velocity over the change in time. So even though the magnitude of this doesn't change, it still has a change in velocity. And so the magnitude of this acceleration for an object moving in a circle is going to be equal to the magnitude of the velocity squared divided by the radius of that circle squared. That's big idea number three. So I'm going to use these three ideas. The total force on an object is equal to mass times acceleration. The gravitational force is equal to, depends on the product of the masses divided by the distance between them squared. And the acceleration for an object moving in a circle is proportional to the velocity squared divided by the radius of the circle. Okay, and that's important because we have the satellite moving, the space station moving in a circle. This is important because there's a gravitational force between these two, and this is important because it makes a connection between these two. Okay, so let's start over. I'm going to redraw this picture, and then we're going to draw the forces on it, and we're going to make everything work. It's going to be great. Okay, so here's my Earth. And this is not to scale. There's a space station. So there is a gravitational force, Fg, pulling on the space station towards the center of the Earth. The magnitude of that, let's call this a radius lowercase r. Let's call the radius of the Earth big R. And let's call this h, which is the altitude above the surface of the Earth. So Fg is going to be equal to g times the mass of the Earth times the mass of the space station divided by r plus h squared. Okay, so here I'm going to put my little note card. This, and I'll bring it back. G is the gravitational constant, 6.67 times 10 to the negative 11th newtons meters squared per kilogram squared. Re is the radius of the Earth, and me is the mass of the Earth. So we can just look these things up. They're just constants. So that's my gravitational force right there. Okay. All I did was put in the mass of the Earth, the mass, I haven't put in the numbers yet. I'll put that in a little bit. And the radius of the Earth plus the altitude. Now, I did say h was 400 kilometers. I'm going to need to convert that to meters because the radius of the Earth is in meters. So this is equal to 400 times 10 to the third meters. Okay, so that's my gravitational force. Now, what does that do? This is the only force acting on the object which causes it to accelerate towards the center of the circle, which is the center of the Earth. Isn't that convenient? So I can set this gravitational force, Fg, equal to ma. So I know this, g, mass of the Earth, mass of the satellite, over r plus h squared. And that's going to be equal to the mass of the satellite. Because I'm talking about the acceleration of the space station times its acceleration. But the acceleration for an object moving in a circle is v squared over r. So this is going to be equal to v squared over r, but r again is r plus h. Okay, so now what we want to do is I want to solve this for v squared, or for v. Okay, so let's just do some algebraic stuff here. Number one, I can divide both sides by ms, the mass of the space station. Cancel, cancel, cancel. Okay, so that's good. Next, I'm going to multiply both sides by r plus h, r plus h. So now I get this side, I write it as v squared equals r plus h, g, mass of the Earth, over r plus h squared. So this cancels with one of those, and I get g, mass of the Earth, over radius of the Earth plus h is equal to v squared. Now to get v, I just take the square root of both sides, and I get v equals the square root of g, mass of the Earth, over the radius of the Earth plus h. That's it. Now I just need to put in my values, so I'll put them over here. G is, I'm going to leave off the units just because it'll make it look a little bit better. 6.67 times 10 to the negative 11th. The mass of the Earth is 5.97, that's a 7, times 10 to the 24th, divided by r plus h. So let's write that out as r as 6.38 times 10 to the 6th plus 400 times 10 to the 3rd. That's it. Okay, so now I just need to put this, I'm going to put this in my calculator and we'll find out this answer. So here's my HP calculator. I know you're jealous. I had to put a little battery modification in there. So I'm just going to put all these numbers in. This uses RPN notation, so I enter the number and then I operate them. And it's just a really nice way of doing it if you don't have an RPN calculator. They do have some calculators, apps for your phone that if you like this. But this is the HP, this one's really old. It's the HP 28S. Okay, so let's enter this number, 6.67 times 10 to the negative 11th. You do also want to be careful about your calculator and making sure you know how to enter scientific notation in your calculator. Okay, so now I'm going to say enter. Now that's in my number in my calculator. Now I'm going to multiply it by this, so I need to enter that one in. 5.97 times 10 to the 24th. I could say enter, or I could just say times. And then it's going to return the result of these two in my first stack right there. Okay, so that is now, this number is that times that. Now down here, I'm going to add those two numbers before I divide. So I'm going to take this number, 6.38 times 10 to the 6th, enter. Now this number, 410 to the 3rd, plus. So now I have that number down here, and I already have this number in my first stack. So now if I just press divide, it's going to divide those two. See, so I didn't have to write down that number. It just kind of saved it. So now let's put divide. Now I need to take the square root of this number. So I just go over here, square root. And I get 7663.6, I guess, meters per second. And that is the velocity that it is moving around the Earth. Let's do one more thing. Let's use that velocity, and now let's find the time it takes to orbit the Earth. Okay, so going back to our circle. Here's the Earth. Here's the space station, not drawn to scale. And I know the velocity. And I know the radius. I'll call that r. Okay, so what do I know? I know the velocity is the change in distance, the magnitude of the velocity of the change in distance over the change in time. So that's going to be 2 pi r over big T. So big T is, we call it a period. And 2 pi r is the circumference of the circle, right? I know if I take 2 times pi times r, that gives me this whole distance. So I can solve this for t, and I get t equals, multiply both sides by t, divide both sides by v, 2 pi r over v. So let's put in our stuff. So I get 2 times pi times r was this number down here. It's going to be 6.38 times 10 to the 6th plus 400 times 10 to the 3rd. All of that over the velocity, 7663. Okay, let's put that in our calculator. Oh, I didn't need to do that. Okay, it's 2, enter. There's a pi button on here, so I can just do pi. Oh, I didn't do that. Drop. So let's say 2, enter. Pi. Now I need to convert that to a number times. Now I need to add these two numbers together. 6.38 times 10 to the 6th, enter. 400 times 10 to the 3rd plus. Now I can multiply that together. Now I can divide by 7663 divided by. And I get a time of 5559 seconds. Okay, but so t equals 5559 seconds. I want to convert that to minutes. So if I say 1 minute is equal to 60 seconds, then I can do a unit conversion. This 1 minute is 60 seconds. So I am multiplying this number by 1. Right? This is the quantity 1, so I'm not changing it. And then here the seconds cancel. So I get 5559 divided by 60. And now over here, I already have that number in there. So let's say 60 divided by. And I get 92.6 minutes. So that's how long it takes the space station to orbit the Earth and make a complete trip. Okay, I don't have anything else to say. Okay, that's it. I'll talk to you guys later.